leave. Okay, so I'm going to talk about PyPy. It's about the Python language. As Jeremy explained, Python, well, Jeremy already described the Python language. So there are essentially three more or less non-experimental versions of the implementation of Python. CPython, which is a straightforward interpreter written in C. Jython, which is essentially the translation of it to Java. And Python, which is essentially a version of it for .NET, the CLR. So what we are working on is PyPy, which is a new Python interpreter, which is rewritten in Python, so using Python as a base language. So PyPy is essentially a very straightforward interpreter as well. There is nothing fancy about it. You have this interpreter that we write, which is just written in Python, a normal interpreter, running on some host runtime. And well, doing some user program, and also we've made some, we use quite a lot of support code for the interpreter at the user level. So of course now, being written in Python, our host runtime must itself be Python. So for experiment, for development purpose and testing purposes, we use CPython standard Python runtime as a host runtime. And of course, now Python being very dynamic, the CPython is a very slow interpreter. PyPy is also a naive interpreter, so it's also very slow. So this is actually slow square too, so I mean, it's like 1,000,000 times slower than C code, this kind of speed.
You're very patient.
And this is a simple picture. The standard, the core is an interpreter. I mean, a classical interpreter. You get some kind of bytecode compiler that translates your source to some bytecode. This is the main loop of the interpreter, switch dispatching based on the bytecode. And we have made an explicit distinction. This so-called object space is actually an object library. So you have, on the one hand, a very rich set of built-in types and semantics of the operation between these built-in types and so on. And this is all encapsulated in this library. And the bytecode interpreter is merely doing calls to this library to actually perform the operations. So essentially, you have an interpreter and this is the domain on which the interpreter runs. And the reason we have made this separation is for flexibility. The way we want to recover performance is by actually applying this is, I mean, it's common knowledge in academic circles that in theory specialization is very cool because you can take an interpreter. So an interpreter is functions that take some user program source and some input data, interprets the whole thing, and you get the result. Now, if you have a source which is known in advance, and the interpreter itself is known in advance as well, then by some kind of compilation, constant propagation, and so on, you can replace interp and source with a single function f, which is optimized for this given source. And it looks very nice. You have compilation for free. Given an interpreter, you can transform it into an optimized function f that will perform the same job. Now, this is very nice. Well, there is a catch. Specialization is actually a very difficult subject. You have a lot of problems. So what we are proposing here with PyPy is actually a kind of practical approach to make exactly this. We have written an interpreter which is really just a naive interpreter, and then we are writing the tools and techniques to actually make this interpreter fast again. So essentially we are transforming the interpreter into a compiler automatically. These same techniques apply for any interpreter. So you can change the language by just writing an interpreter for another language, and we have the techniques and the frameworks to transform this interpreter into a compiler for whatever language you wrote the interpreter for. And this is in more details how it works. One way to do specialization is by, or compilation by the way, one way to do specialization is by abstract interpretation. If you have a source program, so let's say this core of my interpreter, the box above, I consider it now as a Python program, which it is itself. I feed this Python program to this other box, which happens to use a Python interpreter, which is convenient. That's coincidence. And by doing abstract interpretation instead of concrete interpretation, you can actually perform specialization. So abstract interpretation is things like, for example, you follow your source program, but instead of actually having real values and actually interpreting the source program with these real values, you have abstract values. For example, types, you propagate types. So for example, you take a program in Python, you feed it input values which are abstract in the sense that they say, oh, I will be an integer, or I will be an object of this class, and you propagate it through the operations, and doing so you do type inference essentially. But it's doing type inference using an abstract interpreter. And this is something new as far as I know. It's actually very possible in practice to do abstract interpretation with the same interpreter as a concrete interpreter. So we have the very same interpreter here, and we just change the domain. We put here an abstract domain. So what this combination does is taking an input program, doing actually abstract interpretation to do type inference on the input program, so type inference on residual code generation, and you get residual code that is low-level code, happens to be C code, could be any more low-level things, yes?
And so if you change your abstraction, you change your compiler.
Here?
Yes.
Yes. This is extremely flexible. You can plug what you want here. Compile whatever aspects you want. So this is essentially a compiler, this box. And this box here is my original virtual machine. So this allows me to compile my virtual machine to C code, let's say. So there is a catch here, is that this kind of abstract interpretation and so on works, is not entirely compatible with extreme dynamism. If you do two things, language like Python, you can do very crazy things that are very difficult to analyze statically. So this translator is actually only able to analyze Python code in which you promise to do not too wild things. And actually it's still useful. So the question is, why are we still using Python here? We could just write it into a more static language. But it's still useful to use Python because Python is so flexible and dynamic, and you can use this dynamism at load time. Techniques is that this is not a source-to-source transformation. This is taking code which is loaded and initialized. So this core here, you load it into an interpreter, you initialize it, you can use whatever dynamism you want to actually create new classes on the fly, whatever you want, based on user configurations, everything. And when everything is ready, this takes a snapshot, essentially, of the state. So you promise you won't use too much dynamism after initialization, and you get a snapshot. And this is really a snapshot. There is no more initialization code in it. So you get an interpreter which loads like this.
In typical interpreters, the dispatch overhead is considerable. I'm wondering, how do you get rid of that, or is it basically just nulled out as you process each byte code?
So this technique so far is only, so you have two things. You have a C Python interpreter. We have PyPy which currently runs on top of it. So this technique is to bring PyPy back at the same level of performance as the existing interpreter.
Okay.
So this creates an interpreter which still has the bytecode loop which was here.